Hi, welcome back to the Applied Thermodynamic and Heat Transfer lesson. Our today's topic is about heat diffusion equation and initial and boundary condition. Before we start, I'd like to remind you again. So there will be a mini quiz at the end of the video, so you need to prepare your notebook and take a note. If it's necessary, you can try to pause the video. However, remember that our lesson time is limited, so you need to always check the time. Okay? If you're ready, let's begin our lesson. So first, it's about the control volume in heat flow field. And I would like to remind you again about the Fourier's law. So the Fourier's law can be written as this term. The equation 1 in three-dimensional Cartesian coordinates, we will have the q double prime as q double prime x, q double prime y, and q double prime z. Remember again, we have the del T operator. It means the T is the temperature distribution function and is depend on the position and the time. So the partial derivative here is to derive the T from the position, not from the time. So the del T means for the x component is round the capital T over round the x. So imagine we have a control volume in a heat flow field. So this one is unsymmetrical volume, and of course, since its volume, so the volume is a finite region of conducting body. Okay, then the volume has a surface. So okay, this is a surface here. So the surface is denoted as capital S, and the R here is called the volume region. Okay, so the R here is equal to the volume. So we have the element of the surface. So since this is the surface of the volume, so we take a small part of the surface is called ds. So ds has two factors. First, the ds itself always perpendicular to its surface, so it's called normal. This is a normal factor from the ds, and there will be a heat flux factor. Okay, please see again this figure. The volumetric heat release. Okay, so we have the volumetric heat release equal to Q dot. Okay, so if there is a source of heat and the energy source, or E dot G, is equal to Q dot multiplied by the dr. Dr, it means the small part of the volume or the region, and there is a heat source called Q dot, and the unit is watt per cubic meter. And this Q dot, the heat release, is distributed through the region R, and the heat conducted out of ds. Okay, so this is, remember, this is ds. So the heat conducted out of ds in terms of the watts, okay, or the heat transfer rate, since the Q double prime is the heat flux, so the heat conducted out of ds should be written as the heat flux multiplied by the surface area of ds. So we can write, this is the vector, this is the dot product of the, so the heat flux dot the surface area. Remember, the unit of the heat flux is watt per square meter, and the unit of the area is square meter. And finally, we can get the watt unit. The heat generated or consumed, okay, the heat generated or consumed with region R. So the heat generated is the Q dot must be added to the total heat flow into S to get the overall heat rate. The overall heat rate means the Q. And the total heat flow, it means the flux multiplied by the area, or Q prime A. Mathematically, it can be written as the equation 4. Okay, so we take the integration here. So this is the integral of surface, and this is the integral of the volume, and this one is for the heat flow or heat rate, and this is for the heat generated. And remember, there will be a minus sign since the heat rate is out of the ds. So if the heat come is positive, if heat out is negative. And remember again, the energy storage, or E dot St, can be calculated from this relation. The change of internal energy, the sensible internal energy, over the time, since the material will not experience a phase change, so there's no latent effect. And we can rewrite the U as term of mCv dt. This is the temperature over time. First, look at the Cv. Okay, Cv means the heat capacity in constant volume. Since the object is incompressible, so we can say that the Cv will be equal to Cp. Cp stands for the heat capacity in the constant pressure, or we can write later as only C. The next part, please see the M M is equal to density of the object multiplied by the volume of the object, and the volume is correspondent of the volume of the region R. And next term is change of the temperature distribution. Remember again, the temperature distribution has a function of the position and time. So we can write into the partial derivative around the temperature over around the time. Finally, this equation, the du over dt, can be written as rho c round the temperature of the round the time multiplied by V. The V is the volume, so we can rearrange again the change to dr, and we take the integral of the region. So we can get finally the equation 6. And we can rearrange the equation 4, this is the equation 4, into this term. You can see this is a negative, multiplied by negative will become positive. And this one is still positive here. Okay? And then we put value from the Q value from equation 6. So it means we put the Q is equal to du over dt. And finally, we have this equation. Okay, this is the exactly the same. Okay, we put this equation and we add this term. Remember, this term is equal to du over dt. And if we rearrange the equation again, we can obtain this relation. See, in the left hand side, okay, this term is put into left hand side. This term is changed to the right hand side. Okay, since this is positive, now it's become negative. And since the right hand side, the integration is the integration of the volume, so we can write the dr is outside the bracket, and we can obtain the equation 7. So this one is the equation 7. To solve it, we introduce called Gauss Theorem. So the Gauss Theorem can convert the surface integral like this. This is the surface integral into a volume integral. How to convert it? Okay, for example, this is a surface integral. By using this theorem, this A, okay, A means some factor, some unit in factor, dot nds will be equal to the volume integral of del dot factor A dr. So we can identify this A, okay, this A with K del T. Okay, so this one is like the A factor. So we will have exactly like this one. Okay, and then the equation 7 can be reduced to this term. Okay, remember this is the A. So del dot is should be and K, okay, K delta, sorry, K del T. Equal to this equation. Sorry, this should be another dr here. Sorry. So del K, this is the A, dr. Okay, I forget put dr here. And finally, we can rearrange the equation into the equation 8. Okay, this one, this term, okay, this one is come from here, and then we put all the equation in the right hand side into the left hand side. So this one become negative and the q dot become positive. So in the in the right hand side is equal to 0. So we can get the equation 8. Okay, this is the equation 8. And since the region R is arbitrary, the integrand must vanish. Therefore, we can get the heat diffusion equation in 3 dimensions. Okay, so this one will be vanished, and also the dr will be vanished. So we will have only this equation. And we arrange again. So the q dot is remain in the left hand side, and the rho c, round the temperature of around the time is to the right hand side. However, this equation has the limitation. First, this is for the incompressible medium and there's no convection. So if the variation K with temperature is small, the K or heat conductivity can be factored out of equation 9. So the equation 9 can be rearranged into this equation. Okay, the del become del square T plus Q dot over K equal to 1 over alpha on the temperature of around the T. And there's another variable here, alpha. So alpha is equal to heat conductivity over density over heat capacity. So the alpha can be called as thermal diffusivity. diffusivity. Okay, this is alpha is thermal diffusivity. Next, this term del square t is equal del dot del t. So this term is called Laplacian. The Laplacian in Cartesian coordinate or x, y, z of del square t can be written as the equation 11. So this is in the Cartesian coordinate. In cylindrical coordinate, the r theta z, however, we will not talk about this in this lesson today. So this is just for your information. You can write the del square t as equation 12. And for the spherical coordinate, again, we will not talk about this in this lesson today. So we have the r theta and pi. Del square t will be equal to this equation. Okay, remember, you only need to use this equation. Okay, so this will be our today's topic. And steady state condition with no change in energy storage. So remember, this is the equation 9 of heat diffusion equation. Sometimes we call it heat equation. We can write in this term, or we can change to del square t plus q dot k over 1 alpha on the temperature over on the time. Okay, this is the same meaning. So we can write this equation. I will erase. Okay, into this term. Okay, remember, this one is for the x, so it means the partial derivative. So it's the second partial derivative. So we can write this one as, since the k is constant, so we can write like this: k del square t over on the x square. And same for the y and z direction. Okay, so I will erase again. Sorry, I will erase again this one. So in one-dimensional x direction, there is no energy generation. So we only take care about one-dimensional, and okay, so this is a special case, no energy generation. So it means this term, okay, this term will equal to 0 because this is for the energy generation. dimension. And this term, okay, this is for the y and z coordinates. So since one dimensional, so only this one is valid. So the equation can be written simple as this equation. And under steady state, and then one dimensional condition with no energy generation, the heat flux is constant in the direction of transfer. So remember, three conditions under steady state, one dimensional condition, and no energy generation. The heat flux is the Q double dash, or in the one dimension is Q double dash X, is constant. So this is constant in the direction of transfer, or mathematically we can write as the change of the heat flux over the position X is equal to 0. And as the summary, please remember this equation. Okay, remember this equation. And the del square T, okay, in the x direction, it can be written, okay, this is in the x direction, can be written as del T, okay, please remember this term. And we have another term is the thermal diffusivity. It's called the alpha. Alpha can be calculated by using the thermal conductivity. This is thermal conductivity. The rho is the density, and C stand for the, sorry, okay, let's go back again, sorry. Okay, this is the heat capacity. Yeah, as you see, we have the mini quiz here, so please pause the video so you can see the table below and take a note. So you need to calculate the diffusivity of the substance. It means you need to calculate the alpha. Okay, means calculate the alpha. So please go to the quiz part, mini quiz part, and select the correct answer. So you will have limited time, remember? So that's all for the first part.